Okay, let's review what it means to find horizontal asymptotes just by looking at the function. And then we'll kind of throw in some of the slant asymptotes as well. So the way we look at horizontal asymptotes is we always compare the degree of the numerator with the degree of the denominator. So just kind of a quick review, kind of reading our textbook, looking at what happens when your degree of your numerator is less than the degree of your denominator. That's going to tell you right away that your horizontal asymptote, and for purposes of abbreviation, I say HA. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is, and remember it's horizontal lines, so we have y equals 0. So right away, all you have to do is inspect, and you can come up with that horizontal asymptote without too much math. Now, a little bit more complicated, but not too bad. If your degree of your numerator is equal to your degree of your denominator, right away you have your horizontal asymptote. You're going to set up a ratio. And what we do, it's always y equals, but it has to do with leading coefficients. So we're going to take the leading coefficient of your numerator. I'm going to have to squeeze this in a little bit. And leading coefficient of your denominator. Pretty much you set it up as a ratio or a fraction, and then if you are inclined to, you can see if it reduces, but you don't really have to do any dividing. Now, last possible case, if your degree of your numerator is greater than your degree of your denominator, then you do not have a horizontal asymptote. So that's kind of nice, but I will let you know that you may have what they call a slant asymptote. Sometimes we abbreviate that with SA. Or you could see in some textbooks, they call it an oblique asymptote, for which I would probably designate as OA. I like slant better because it makes more sense. It's a slanted line, but just in case you see that in another textbook, there you go. And it only has a slant asymptote if the degree of the numerator is exactly 1 degree higher than denominator. And I'll see if we can designate or kind of show that in one of the examples below so that we can really talk about what that means. And it has to be exactly 1 degree higher than that of the denominator. So let's see if any of these 3 cases give us that. So this particular example, we have A, B, and C. We're identifying the horizontal or slant asymptote. And pretty much, I always start off by just asking myself, do we have horizontal asymptotes at all? So look at part A. What we're going to do is we notice that we're looking at the degree of the numerator over the degree of the denominator. And we're just kind of seeing, it looks like they're all in descending order, but you're looking at the leading terms pretty much to help you out. And notice, I'll kind of note to you, degree of numerator. What is it? Well, it's the highest power you see. It's equal to 4. And the degree of the denominator happens to be the same thing. So they're both equal. So degree of numerator is equal to degree of denominator. So what does that tell us? We are at this case up here. That tells us we do have a horizontal asymptote. It exists, and it is found by setting up a ratio of the leading coefficients. And so our leading coefficients, just so that we can see that together, leading coefficient, we have a 3 on the numerator over 12 on the denominator. I made that fraction bar a little too big, huh? Let's see if I can make it a little prettier for y'all. And normally what would happen, you kind of see that 3 over 12, it reduces to 1/4. So we would probably take the reduced version. So now we have our horizontal asymptote is actually y equals 1/4. So that would be kind of hard to tell if you were graphing this and you're trying to do this by inspection. But it's really cool that the formula or the function itself leads you to understand the exact value of the horizontal asymptote. Super cool. Now let's take a look at part B. We'll start over again, and this is kind of going through the 3 categories. Again, we're going to compare the degree of the numerator with the degree of the denominator. And that has us looking at leading terms. They happen to all be in descending order, so that's super cool as well. So just kind of talk about it. Your degree, part B, degree of your numerator, I'm going to abbreviate, versus your degree of your denominator. And we know that if we're looking at the coefficients, or not the coefficients, the exponents, the degree of the numerator is smaller than the degree of the denominator. We have a 2 versus a 3. So we have the case over here. The degree of the numerator is less than the degree of the denominator. So right away, nope, not too much math needed. Your horizontal asymptote is y equals 0. So that was fast. That's kind of nice. Okay, so we're almost there. Let me move this over. Oh, not that much. See if I can do this. Sometimes it gets in the way of the other problems. So we have that part B going on. Okay, so let's look at part C. We'll do the same thing, just comparing the degree of the numerator with the degree of the denominator. And if you all look with me, right away, my degree of my numerator, and let me see if I can abbreviate because I know I'm going to run out of space. So DEG for degree. So degree of numerator versus the degree of the denominator. Whoops. Let's make sure we get that on camera. So again, look at your leading terms. And I know we have this squeezed in there. But I have a x squared in the numerator. So that degree of the numerator is 2 versus the degree of the denominator is just an x. So that exponent on that x is a 1. So we have ourselves the degree of the numerator is greater than the degree of the denominator. And that is that third case that we listed. So right away, just from that, we know we don't have a horizontal asymptote. So if they're asking you to address that, you have to say there's none or there's no HA. But check it out. 2 is 1 more than 1. Nice little math there for you. But so if you run into this case, it's exactly 1 degree higher. Degree of numerator is exactly 1 degree higher than the degree of the denominator. We do have our case of the slant asymptote. And maybe I don't want to spell that out. So we do have an SA going on. I'd like to write that a little nicer for you. And if you're interested to find the slant asymptote, what you do is you divide the denominator into the numerator. So we kind of use division. So we can do this by saying what is x minus 3? Divide that into x squared minus 4x minus 5. Now you can use long division, that always works. But I kind of noticed that my divisor is in the form, it's a kind of a linear factor or linear divisor. So I'd rather use a synthetic division. So I can do that as well. I'll kind of restart. Synthetic division is a nice shortcut when you have this case. But if you didn't have a linear divisor, you'd have to use this long division. Well, let's do the synthetic, save us some time. So synthetic division, we know that the divisor is x minus 3, so that tells us that we'll be looking at 3. It's the opposite of what we see. And we're going to list our coefficients of our numerator, and everything's in descending order, so we're good to go. So the coefficient of x squared is 1. The coefficient of x is negative 4. And we have a constant, that's negative 5. And so with synthetic division, save some space too, because I was running out of it. Synthetic division, we bring down the 1, multiply it with the 3. So what happens? 1 times 3 is 3. We write that result underneath the negative 4. We add those, we have a negative 1. And negative 1 times positive 3 is a negative 3. And this will give us our remainder, which is negative 8. Now, as far as slant asymptotes are concerned, perhaps when we get to calculus, we'll talk about, what's the real reason why we're able to ignore the remainder. But for purposes of our particular slant asymptote, it is a line, a slanted line. And all of the slanted lines, I'm going to move over because I want a little more space. All of the slanted lines come in the form, we love this slope-intercept form, y equals mx plus b. And that mx plus b part, the most important part, that's coming from your result of your synthetic division. So remember, if you divided x minus 3 into x squared, you drop the power down by 1. So our result of the division, we should have x minus 1. And so what that means is the mx plus b part becomes 1x minus 1. And of course, if you're writing the equation of your line, it'd be y equals x minus 1. And that, my friends, is your slant asymptote. So I think that's a super cool way to figure that out. You guys want to verify it? We can kind of see how this looks with a TI. So let's pull that up and see if we're really getting these. And I'll go backwards for the sake of space. Sometimes it takes a little longer to pull that TI up for ourselves. Here we go, Smart View coming along. And what I want to do, I'll move the viewing window over. I'll keep it the same. I'd like to just kind of look at the last one, part C, and I'll let you do the others if you want to check for yourself to see, does that make sense? But let's look at what we had again. I have to look at x squared minus 4x minus 5 in the numerator. So if we're going to check that with our TI, normally when we type in rational functions, we have the whole numerator in parentheses. So x squared minus 4x minus 5, close the parenthesis. And let's double check. I know it's going to be divided by, and we're going to open up that parenthesis in the denominator, but let's make sure we have the right signs again. I'm always a little paranoid when I have to switch back and forth with screens, but it is x squared minus 4x minus 5. And the denominator is x minus 3. So let's take a look at that. We have x minus 3. And let's graph it. And we could kind of see, okay, What I want to kind of verify is it does look like we have some slant going on. I don't know if you guys can see me point to this with the particular cursor. But remember, we thought our slant asymptote was y equals x minus 1. So we can kind of see what the behavior of the function around that is. And I'll do this in red. Now, this is not part of the graph. It's the behavior of the graph. So, if you want me to be fancy, I'll be fancy for you. I could actually change the style to dash line, kind of. There it is. Well, maybe not. Let me go with the equals. Ah, there we go. Okay, it's not working out the way I wanted to, but I'll do it with, how do you say, maybe a slightly smaller line. I guess it depends what type of calculator you have. It's not being very nice to me right now. All right, my intentions were good, but I guess it didn't work on my viewing screen, but that happens. So I just made it maybe a less bold line, but I just want to show you how cool this is. Let's graph it. Check it out, y equals x minus 1. We can actually tell just by looking at the behavior of our graph. As our blue graph approaches this red line, that's the slant asymptote, you can kind of see it's getting very, very, very close, but maybe just hugging it and never crossing it. Same thing over here as your x values for your particular function, as they get closer to that red line or the slant asymptote, you start to see right above on the side, I could say right side for you, that your graph is going to hug it. And if you want to play with the window to see the behavior just a little bit more, feel free to. I always like to use my TI to verify, so I can kind of see what's happening a little closer to the top, and you start to see a little more to the right of the screen. Yeah, it's getting very, very close, and I can, feel free, play with your window a little bit more. Maybe I need to make my X max a little larger. Don't go too crazy, but you start to see, oh yeah, for those larger values of X. As we get really closer to this branch, you start to see that the function itself in blue approaches this slant asymptote, but never crosses. And the same thing could happen for the left side if you're interested. So that kind of gives me, like, I feel better about myself because I figure out, like, yeah, I did that slant asymptote quite nicely. Just in case maybe you mess up on your math, you can use your TI to help you verify that. So feel free, if you want to explore about the horizontal asymptotes for part A and part B, feel free to punch those into your TI, and you can kind of feel a little better about putting your final answer down. I hope this helps. I will see you in the next example.